Club. So log base 3 of 42. If you remember, and it's been almost a week, so maybe not, we'll see. Whenever you're finding a log, you're determining what power the base has to be raised to in order to give the argument of the log. So it's asking what power does 3 need to be raised to in order to equal 42. All right. So that's what that notation is telling us or asking us. Right. It's just weird notation. Now, in terms of computation, it's not bad. You go into Desmos or the TI calculator, whichever you prefer. Go to function. Under miscellaneous, you have the one that says log with a little subscript of a. You just type in your values here. We got a 3. You got a 42. They told us to round to 4 decimal places, so I was already on the lookout for a funky decimal. Right? So they're saying it's 3 point. If I go to 4 decimal places, 3.4022. Right? So it's approximately 3.4022. Right? So I can verify this pretty quickly because, again, this logarithm is asking us to determine what power 3 needs to be raised to in order to give a result of 42. So if I take 3 and raise it to that power, I'll just use the rounded form. It should give me something that rounds to 42, and it does. Right? So that's a quick way of checking to make sure your answer makes sense. Right? It's not something that you'd be expected to figure out in your head because, one, you have the technology. Even if it's a TI calculator, it's still a calculator, right? But alternatively, it's just to 4 decimal places. So, even if they didn't say, or even if they said you can't use a calculator, you'd look at it and say, well, I don't know how to do this. When you're giving me these rounding instructions, 4 decimal places, am I supposed to guess that? It's not practical. All right. So for number 6, it's saying what power does 1/2 need to be raised to in order to give you a 5? So it's really just a matter, and I'll just do this. I'll do this using the keyboard just so you see. You don't always have to go looking for the function. Log, log. It starts off in italics, but once it recognizes it as a programmed function in Desmos, it turns italics into ordinary font. And that little AB right next to the 1, 2, 3, the 1, 2, 3 in the lower left-hand corner, then the A sub B. You tap on that, it makes a little subscript. You could type in 1/2. Well, I'll put in 0.5. But sometimes it has a hard time with the fractions as a subscript. But log base 0.5, 0.5, 1/2, same thing, of 5, and you get a result of about -2.3219. And again, we can verify this pretty easily by saying, all right, if I take 1/2 and raise it to a power, that power should be sufficient to give me a result of 5. Right? So let's see if -2.3219 gets the job done. And it does give us a value that would round to a 5. So we're in pretty good shape there. All right. So whether you want to type it in or use the log function in your calculator, either way, you're going to get the answer. All right. So 0.00098. And so approximately -3.86. It'll go to 666. All right. Now, the remaining questions all involve equations in some capacity, or at least on this page. So we have to do a couple of steps here. Some are easier than others. All of these can be solved using a graph, like a graphical approach, but some of them it's just kind of overkill to do it that way. Like I'll show you real quick, because it's always a good idea to kind of have this in mind, and people forget about it all the time, and even worse, they kind of dismiss this as like, oh, this guy's going on and on about this Desmos crap again. Just show us how to do it by hand, it would be good. But this is a strategy that'll work. You may hardly ever use it, but the one time you need it, maybe for all the marbles, you know, it might be for that one question on a test that gets your grade into the A range, or, you know, maybe you're borderline passing fail. You know, like we don't want to think about that. We want to think about the positives. But if you ever have an equation and you know that it's a function related equation, as in the equation itself is that of a function, right? And so far in this course, that's all we're working with. We won't get to non-function stuff until unit 3, right? So we're not really worried about that at this point. You can always solve your equation by taking the left side and writing it in as one equation, y equals log base 2 of x, and then taking the second side, the other side really, and putting that in as a second equation, all right? And then find the intersection. Now, I can't promise the answer is going to be pretty, but you'll always get an answer, right? So what I would do is I would type this in, y equals log base 2 of x, what a log base 2 of x function looks like. And I would type in y equals -3 all right, so y equals log base 2 of x, left side of the equation, y equals -3, which is the right side of the equation, and see where they intersect. All right, they look like they intersect right here. All right, so I'm looking for the x value for which they intersect, because you know I'm solving each equation, right? The equation here, the independent variable is x. I need to find the value of x. So x would be equal to 0.125. If you need that as a fraction, I mean, you just type in 0.125, 125, tap on that little fraction icon, and you get 1/8. All right. Now, if it's a hideously ugly answer like one of these puppies up here, different story. But that's not the case here. We actually get a pretty clean answer out.
Do you have to leave your answer in fraction form?
You got to be prepared to go whichever direction the question asks you to. So sometimes it'll say to round it. This one said, and round answers to 4 decimal places where appropriate or where necessary. So here we would round it. We'd actually throw a 0 on at the end because it said to 4 decimal places. But some questions will say represent your answer in simplest fraction form. So you got to be prepared to go either way.
Professor, could I say 2 to the -3rd, or you want the 1/8?
If the directions don't say simplest fraction form, you could write it any way you want.
Okay.
I mean, aside from like, let me clarify that. If the question doesn't say to write your answer in a specific form, you could write it any way you want. So this one said decimal. So
thank you.
No
Professor,
problem.
is there an easy way to do 0.1250 and have Desmos or the TI-83 calculator give you 1/8? Like, let's say that like I couldn't. Okay, so it does it for you.
Yeah, you just gotta
Right.
tap on that little fraction icon.
Thank you, because like I couldn't figure out like how to make it read like that. Thank you.
Yeah, no problem. So let me show you the more analytic way of doing this, the quote unquote by hand way. So log, we're given log base 2 of x is equal to -3. Yeah. So we talked about this last time, and I'll zoom back in a sec, but we have this little, it's not really a mnemonic, it's just more like a rule. the conversion between log form and exponential form, but it's actually pretty easy to go from log form to exponential form. It's the other way around. When people get jammed up on this, that's where they get jammed up, right? But going from log to exponential form is not too bad, because this too is the base of the logarithm. The base of the log should always be the same as the base of the exponential. Right? And then from there, we work our way around in a circular pattern. Right? So we would take the 2, raise it to the negative third power, and make it equal to x. Right? So that 2 is occupying the role of the base in both situations. It's just everything else is going to change up accordingly. But once you make that adjustment, it's pretty consistent in the way that you represent your conversions, right? So it's always base, power, result in that circular pattern. And I'll show you. Number 11 is very similar to that. You start off with the 6. That's your base. Let me write that with a thicker marker. You work your way around by raising it to the negative second. And make your result equal to x. And in both of these cases, you have an answer. It's just a question of how they want you to represent your answer. Right? So 2 to the negative third, that could be 0.125. That could be 1/8. All right. It all depends on how they want the answer. 6 to the negative second, same idea. If I take 6 and raise it to the negative second power, I get this funky decimal. Not very appealing to look at, but it is repeating, which means it's fractionable. Right. But all I have to do is tap on that fraction icon and it'll convert it over for me if I didn't happen to know what the value was. Right. This is one of those instances where I probably wouldn't want to round it, because I have actually a much cleaner decimal equivalent available. So why not use the clean decimal equivalent? It makes life a little bit easier. All right. Now, number 13 is along the same lines, so I might as well just bang that one out real quick. Right. There's a fair few of them that are along the same lines, in that if you follow this technique, it goes pretty quickly. The issue is knowing when you need to find this or use this technique to find a different form of the logarithm. So here I have x as my base. I'm going to work my way around the circle. I'm going to raise that x to the 1/2 power. And the result is going to be equal to 4. All right. Now, this technique, whether it's in number 8, number 11, number 13, they all have something in common. And that was the variable x was part of the logarithm. Right. The idea is that we want to try to release the variable from the logarithm. This technique does that. This technique releases the variable from the log. But if you compare that to something like number 12, you look at that and say, well, I don't want to convert that. I don't want to use this technique because the x it's not trapped within the log. It's not imprisoned in the logarithm. This I just chuck right into the calculator and call it a day. So I would just put in my log base 7, the 1/49, and you get a nice clean -2. Now, it also kind of begs the question of, if that answer is so nice and clean, is there a way that we could have gotten that without using the calculator at all? And that comes back to the properties of logarithms. right? In a lot of ways, and we do have to answer number 13 completely in a sec, but just kind of going with this thought here, there often is a nice, easy way of using properties to come up with solutions for logarithms. But if you go to the word problems a couple pages down the line, you see that they're not all tailor-made for something like that. But in this case, it's kind of interesting because if you look at this expression, we could apply a couple of properties and it'll clean up really, really nicely, right? One is that I see a quotient here, so I would apply the quotient rule. All right, so if I apply the quotient rule, I'd be looking at log base 7 of 1 minus log base 7 of 49. All right, quotients become subtractions. All right, so if you see division contained within the logarithm, you can break up the logarithm, making your division into a subtraction. All right, the log of 1, regardless of what the base is always going to be equal to 0. All right. Now, this next step is a little bit more intuitive. It's a little more number sensey, but it's actually kind of cool. So that 49 happens to be a power of 7. Okay. Another way I could represent 49 is by calling it 7 squared. The only reason I'm thinking to do that is because my base here is a 7, right? And you'll see how that plays out in a second. So 0 minus log base 7 of 7 squared. In the next step, I can actually apply the power rule for logarithms. All right, I could apply the power rule for logarithms, which would make this 0 minus 2 log base 7 of 7. Now, as it turns out, if a log has an argument and a base that are exactly the same, so like in this case, log base 7 of 7, you could have log base 2 of 2, log base 20 of 20. If the two numbers that make up the log are the same, it goes to 1 because of what we were talking about before, wherever it is. When I say something like the log base 3 of 42, I'm asking what power does 3 need to be raised to in order to equal 42? In this case, I'm saying what power does 7 have to be raised to in order to equal 7? So that's what that's asking us to figure out. Whenever, again, never lose sight of what the definition of a logarithm is. Because it's very easy to say, all right, I'm going to put the log into the calculator. It's going to give me an answer. But if you don't know what it is intuitively that you're looking for, then it doesn't really tell you much, right? So if you look at this and say, okay, every step of the way, what power does 7 need to be raised to in order to equal 7? You should come back with a 1. 7 to the first power is equal to 1. So this would become 0 minus 2 times 1, which is equal to -2, which is what we got using the technology. But this is kind of, this is the genesis of that. But that also tells us that even way back in this step up here, all the way back up here, we could have applied that same idea, right? Because just this expression, I'll highlight it for you. If you know what you're looking at, if you know what the definition is of the thing that you're looking at, you can always kind of reason your way through it. What power does 7 have to be raised to give 49? 2. The first part became a 0. 0 minus 2, -2. Okay, so there's ways to get this without a calculator. You're not going to be forced to do that. But down the line, if you want to have the intuitive understanding of functions that'll allow you to be successful in calculus and beyond, this is the kind of stuff that you want to start thinking about. Okay? Just to put a ribbon on number 13, we never solved for x. In order to get rid of that power of 1/2, I can raise both sides to a power of 2. And that's one of the properties of exponents. If you raise a power to a power, you multiply the powers. Power to a power, you multiply the powers. It's very alliterative. Right? But 1/2 times 2 is 1. So this is really x. On the right is 16. It actually became a pretty easy problem once we released the variable from the logarithm. Doesn't always play out that way, but it's nice when it does. All right. Now, the remaining problems are all multi-step problems. That's why I did these ones first. Although it looks like number 12 is a multi-step problem. It wasn't. We did that in one step. We chucked it into the calculator. All this extra stuff over here was me showing you, like, in an alternate universe, how you could have tackled this problem. Right? Slash back in the 80s when we weren't allowed to use calculators. Oh, it was 90s for me, but still. So, number 9, we have multiple logs on one side of an equation. Right? Whenever you're solving a log equation and there's multiple logs, our first goal should be to consolidate our logs. All right? We want to compress them down into a single logarithm where possible. All right? So this is actually an expanded product rule. This is an expanded product rule. And what I mean by that is, this is what happened after the product rule was applied. Originally, it was a different expression. And somebody applied the product rule, the product rule, and this gave this as a result. So let me just remind you what the product rule is. If you have log base b of some factor m multiplied by some factor n, we're looking at log base b of m plus log base b of n. Very similar conceptually to the quotient rule, except addition instead of subtraction. All right. So what's happening here is we actually already have this part. This is what they gave us. They gave us this piece. We need to work our way back to this piece. So when you're putting the two logs together to make a single logarithm, the first thing you would do is rewrite it as log base 5, knowing that the sum was the result of something that it was a product previously and it became a sum, then the two arguments must be multiplied in order to give that single log. Okay. So if you kind of follow this in reverse order, you'd say, all right, if I were presented with this as a question, I'd say, all right, well, what do I want to do if I want to expand this out? I'd take the log of this piece plus the log of that piece, which would give me this expression here. All right. So that's how you would compress it down. But then if you look at the left side and compare it to the right side, you see that the only thing that varies from left to right is the argument of the logarithm. Okay. So I have the 4x and I have the 36. I got a log base 5 on both sides. That's consistent. I'm not worried about that. On the left side, I have a 4x. On the right side, I have a 36. So if I set those two things equal to one another, so I'm just going to pull them out. It's kind of a misstatement, because I don't know how many people have a ton of experience with logarithms. Some definitely more than others, but people have learned in the past that at this point you would drop the logs. That is completely, totally, and utterly incorrect. It's not even close to right. Right? What we're doing is we're extracting the 4x and the 36 to make an equation out of that. The logs aren't going anywhere. Right? Because what people will do is they'll be like, all right, cancel the logs. You can't cancel them because it's not a product. It's not log base 5 times 4x, it's log base 5 of 4x. It's function notation. All right. We're saying that we have a function of 4x and the function is the log function. Right? You can't just cancel it. That'd be like if you had something like f of x is equal to x, and somebody came along and said, all right, let me cancel the x's. It doesn't work that way because this is notation. You just can't do that. Right? It's the vocabulary. Right? So we extract the 4x, we extract the 36, solve, you get x equals 9. And that tells us that the log base 5 of 4 times 9, because that's our x value, get this to look halfway decent, would be equal to the log base 5 of 36. Which would be a true sentence, true mathematical sentence.
Can you explain again why we're allowed to just multiply the 4 and the x together?
Because what we're doing is we're applying the product rule for logarithms. So what we were given was this expression here, log base b of m plus log base b of n. What they're telling us is that, and I'll just get rid of this arrow for a second. They're telling us that the m value is really the same as 4. And the n value is really the same as x. And those b's are really 5. I'll just make little 5s here.
Okay, I see now.
Okay. I might as well just throw out the rest of the way. So that's a 4, and that's an x, and that's a 5.
Thank you.
No problem. All right, so that's using a logarithmic property. So along those lines, we have number 15, and numbers 10 and 14 are similar, so we'll do those together. One after the other. But number 15, you see that we have multiple logs on either side of the equation. So we're going to use a similar idea. This time we're going to use the quotient rule because we have subtraction. Right? So I'll just refresh your memory on the quotient rule. That's log base b of m divided by n is equal to log base b of m minus log base b of n. All right. So what they're telling us, just focusing on one side of the equation for now, they're telling us that the x, actually, let me do it this way. The x is the m value. The 5 is the n value. And again, just like the previous case, we're working backwards. We have the expansion, we want to compress it down, right? So we're going to take that m and put it over the n. So the left side of the equation is now going to become log. They didn't give us a base. Whenever they don't write a base, it's an assumed base 10, okay? So this is actually a base 10 logarithm. I just had to wait for that motorcycle to go past. Actually, I'm pretty sure that's not a motorcycle. I'm pretty sure it's a guy who just has a crappy muffler. Right on cue. Muffler backfires. You know, like one of the little pet peeves that I have, actually it's pet peeve number 57. People who have crappy mufflers but pretend that they're sport mufflers.
No, people just feel cool and they straight pipe or remove their cats because it's loud, but they go like 2 miles an hour and it sounds like a roller coaster.
Yeah, well, that's the thing. It's like they don't know. Maybe they don't know what it's supposed to sound like. It definitely doesn't sound like a race car. It sounds
You just
like
want to flex. It's for attention.
Yeah,
Nah,
but it's a
man, I'm just
See it
malfunctioning
all the
poor.
car. It's like a piece of crap car. Like,
Yeah, usually on Civic. Sorry if
Yeah.
anyone has one. It's the
Nah,
case
man, we're just poor. We can't afford the muffler. I'm telling you.
though.
hey, I've been in a situation where I couldn't afford the replacement muffler. That's a different story. But you
Yeah,
always
that's
know when I can't afford the replacement because you can see the sparks on the road underneath the car from where the pipe is hanging down. So-
Yeah, I had a perforation in my exhaust system. And I sounded just like that. I got really scared one night because it was like 4 a.m. I had to wake up for like a thing, and then yeah, it was just super loud. But yeah, I got to
Yeah.
fix the media.
Yeah, and you find out
Yes.
very quickly that duct tape doesn't
Benefit
get the job done.
Yeah.
So in this case, we're looking at my pen stopped kind of working the way I wanted to, but we're looking at logs that have bases that are not written here. So they're assumed base 10s, right? That's just kind of I don't even know. I was going to say it's a rule, but it's just something that somebody decided upon a long time ago. That, you know what, it's such a common logarithm that we're just gonna write it without the base, because I mean, we're so often writing a base 10 logarithm that everybody will just know that when you don't write the base, it's just a base 10, right? And in fact, that's what they call it. They call it the common log. I don't know why this spot isn't going away. I've tried erasing it like 1,000 times. Try it this way. No, screenshot. It's saying it's not there, but it's there. And I'm just going to write over it with a thicker. Oh, now it worked. Okay, good. So log, you can write it with or without the base 10, but it's going to be log of x over 5. That's what the whole left side boils down to. Now on the right side, we also have a subtraction. I'm going to get my highlighters going again. That subtraction involves a 2 and an x minus 3. All right, so the 2 takes on the role of the m, and the x minus 3 takes on the role of the n. But it's still the same idea where we're compressing our logs down into a single log. All right, so log of 2 over x minus 3 with a nice fat equal sign in between. And just like I was saying before, once you have it as a single log on the left and a single log on the right, the only thing that's going to vary would be whatever is contained within the logarithm. So we extract that. So we pull that information out, because if we could determine the value or values, sometimes multiple values, of x that allow the argument on the left side to be the same as the argument on the right, then we'll have equality. So x over 5 is equal to 2 over x minus 3. Now you solve this any way you want, but the most likely approach, if you're thinking of an algebraic solution, would involve cross multiplying, because it is a proportion. Right? But I'll take this opportunity to remind you that this isn't an algebra course, so I don't need to see the algebra. Right? I just need to see the solution from here on out. You know, the skill that I need you to demonstrate, you would have already demonstrated by the time you got to this step. Right? After that, it's however you want to solve it is up to you. But if you do choose to cross multiply, it'd be x times x minus 3 is equal to 10. Looking quadratic, so I distribute, apply my distributive property of multiplication over addition. So x squared minus 3x equals 10. Quadratic, you want to get everything over to the same side. You get x squared minus 3x minus 10 equals 0. Now we're at the point where it's like, all right, now let me pick my favorite way of solving a quadratic. Whether it's factoring, completing the square, or quadratic formula, that's up to you. But this one is factorable. X minus 5, x plus 2. And when you set each factor equal to 0 and solve, you get x equals 5 and x equals a negative 2. But we do have to be careful when it comes to logarithms. And we talked about this very early on last class. That means it might as well be a lifetime ago at this point. But logs don't exist for all values of x. So there is a domain consideration that we have to keep in mind, right? So we got to look at each piece here. We have common log of x. We got to see if the number 5 and the number 2, number negative 2 would make sense in each logarithm. Anywhere where there's an x, we have to plug in these numbers and make sure that they give us a defined value, right? So I'll take first the 5, log. It's a common log, so I could just type in log of 5. It gives me a number. Doesn't matter what the number is as long as it gives me a number. All right. But then when I go to plug in a negative 2, it gives me undefined. Right. So I was fine with the 5, but the negative 2 doesn't work. Right. So even though we got it as a solution, it's what we call an extraneous solution. The only actual answer to this problem is x equals 5. All right. Always a good idea to attack these problems using multiple approaches, because you could run into an issue like this where if you don't think to check your answers in the original equation, you might miss out on something like this. All right. So what I would do is, just going back to what we did with number 8, I would put the left side in as one equation. So y equals the log, ordinary common log, of x minus log of 5. Good looking function right there. Then y equals, I put my right hand side in, y equals log of 2 minus log of x minus 3. So we got two graphs, two log functions. Neither of them exist for negative values. If you look at it, I mean, they're not even going anywhere near the third and fourth, second and third quadrants, right? But they do intersect, and they only intersect at this one location, the x value of 5, right? They don't intersect at x equals negative 2. In fact, neither of the graphs exist at x equals negative 2. I'll plot x equals negative 2. I'll show you that one. X equals negative 2 is all the way over here. We'll make it dashed. That's x equals negative 2. I don't see any graph over there. I don't see any of the black graph. I don't see any of the purple graph. Right now, it is possible that maybe we're just not looking at a complete graph. Maybe there's some stuff that's off the screen. So I'll zoom out a lot and see. You see these things, they don't go anywhere near that red vertical line. So there's no reason to think that negative 2 would be a solution. All right. So when in doubt, pop it into Desmos, have a quick look at what the solution ought to be, and make sure that you're tailoring your analytic solution to that value. In the case of number 9, we didn't bother checking because we got a nice clean x equals 9. There was no cause for concern. All right. But you'll see, I mean, there's more problems like this. A couple of instances where you have, like a 5 minus x in number 18, you could run into a little bit of a problem there if you're not careful. And some of them are a little bit spicier, like numbers 22, 23, right? But for now, let's tackle numbers 10 and 14. Those are asking us, and at first glance, you look at it and say, in both cases, they're asking us to solve for x, obviously, but they're in both cases presented without logarithms, which should be kind of alarming, right? Because we're working on this concept of logarithms. We're trying to understand this concept of logarithms. And then you see two problems that don't involve logarithms. And you're like, all right, what's going on with this? These are actually the more challenging type problems because they require a logarithm to solve, but they don't write it in logarithmic form. You need to be able to recognize that there are circumstances in which you would have to introduce a logarithm in order to get a solution, right? So if there is a variable in an exponent, you will need a logarithm to solve the equation. So if there is a variable in the exponent, so if there's a variable in the exponent, you're going to need a log in order to solve the equation. So then it's like, okay, cool, that's great news. Now how the hell do we do that? Understood. We're getting there. So first thing I would want to do is get rid of anything that seems extraneous. Overuse a term. I got 1000 is equal to 75 e to the 0.5x. That 75 doesn't really need to be there. I could divide that out. So I just do a quick division. 1000 divided by 75. You got this funky decimal. I'm not overly concerned by that because I see a little fraction icon next to it. Tap on the fraction icon, 40/3. It's not pretty, but it'll do the job. We got 40/3 is equal to e to the negative, or e to the 0.5x. But that I would rewrite. I'm going to shrink this down a little bit so it doesn't get too. Actually, it already is kind of shrunk. Let me just move it. Let's try to clean it up a little bit anyway. So I'm going to rewrite this as e to the 0.5x is equal to 40/3. Wherever possible, I like to have my x on the left-hand side. Right. It makes it easier to convert into log form, and then from there to actually solve. Right. So if I want to convert this to a logarithm, what I would do is first identify what the base is supposed to be. The base of a log and the base of an exponential are always the same. Right. So I'm looking at log base e right? So I got my base. Now I need my logarithm to be established in such a way that if I were to convert back, it would get me to this exponential form, right? E to the 0.5x is equal to 40/3, right? So I think about my exponential expression kind of in a reverse pattern. If you think about what we did over here, we took the base, we raised it to the power, and we set it equal to whatever was contained within the logarithm. And that gave us our exponential. So I'm going to do the same thing, base raised to the power, and the result is going to be contained within the logarithm. All right, so then I would compare that to what I'm given in exponential form. If I'm taking that e and raising it to some power to get a result within the logarithm, that power must have been the 0.5x. Because again, if you follow that circular pattern, base raised to the power equals the result, it would necessarily be the case that e has to be raised to the 0.5x, and then the whole thing would be equal to the 40 over 3. So here's my 40 over 3. That would go there. A little thinner. So it's just a matter of converting it, but knowing the structure and how they relate to one another allows you to make that conversion. Now, what a lot of people have said to me has worked in the past, and it's debatable. You know, you might completely disagree with this. They say, all right, I place my base where it's supposed to go. So here's my base, my E. I place that where it's supposed to go. I take this and I put it where it's supposed to go within the log. It goes down here, right? And then I just take these two things and I switch them. All right, so I take this, put it here, take this and put it here. I don't know, but that I didn't really love that approach, but people say that it works beautifully for them. Right? Whatever works for you. As long as you can get from one form to the other, you're fine. I mean, there's that Venn relationship where it's again log base b. No, I have it written up here. Right, but I'll write it again. But you have the exponential base exponent number, and then you just know that it goes back the other way. So BNE corresponds with B raised to the E equals N. Right. So this is just know this rule. Right. If you're a rule person, you have something. If you're more intuitive, then you have something. Hopefully everybody has a little something. Right. Once you have a handle on that, then something like number 14 isn't going to be that bad, right? But to finish this one up, like the left side is all calculator work. The right side, I just got that coefficient of 0.5. Just bear in mind, a log base E is the same as a natural log. That could simplify things a little bit. Divide both sides by 0.5. And I'd have my answer, x is equal to whatever this results in. So I'd say ln (40 divided by 3). That answer divided by 0.5. And now we have our result of about 5.1805. All right, definitely takes a little doing. And like I said, these are the more intricate types of problems because they're not just kind of tailor-made for you with the logarithm just kind of thrown at you where it's like, all right, now just use some properties, get an answer. You got to kind of think about, all right, what's my strategy? But if you have a variable in an exponent, you're going to need a log. So it really just ends up being the case that you're going to have to convert your exponential into log form. All right. It's the same idea for number 14. Like I was saying, you have your base. All right. So log base 10 of something. All right. That's supposed to be a rectangle. Is equal to something else. So when you're converting this exponential into logarithmic form, if you work your way around, you would say, all right, 10 to some power, there's always a power, gives the result in the exponential. So 10 to the x power gives 27.5. Also, if you know the definition of a logarithm, you can figure this out without knowing any kind of shortcut rules to convert into log form. because early on I was saying, and it's still written right here, when you see something like log base 7 of 7, I'm saying, what power does 7 need to be raised to in order to equal a 7? This is really saying, what power does 10 need to be raised to in order to equal 27.5? If you know the definition of a logarithm, that tells you, oh, wait, log base 10 of 27.5. It means the same thing, right? Just by being able to read the equation and understand what it's really asking you to figure out, you're able to convert it over into log form. Either way, I mean, so many different ways to get there. Bottom line is, we need a log base 10 of 27.5. So X is going to be about 1.4393. All right. So hopefully that was somewhat helpful. And I always like to chunk this lesson into smaller pieces because it doesn't serve any purpose for me to go through like 20 examples all in one shot. So instead I did like 8 examples all in one shot. And then I'm going to ask you to take a look at the remaining examples on the next page. I'm doing that same crazy thing I did with the stars last time. I don't know why. I can't stop myself sometimes. But you should now be fairly well qualified to be able to tackle these questions. We'll go over them a little bit quicker next time, but then we'll tackle some word problems also. All right, those word problems, I mean, they're not bad. It's just you need to be able to have a good handle on this stuff in order to be able to tackle the word problems, right? Very important, right? Because as you know, whenever, and honestly, most people kind of, if they struggle with word problems, they all struggle with the same thing. I know what to do with the equation once I have the equation. I struggle with writing the equation to begin with. All right. So
This is my problem.
yeah,
100%.
almost everybody who struggles with word problems, that's the number one thing. So I'll show you how to decode those problems in order to get equations that you can then solve. The issue is those equations are going to require these techniques in their solution. So getting good practice with this stuff is going to be really, well, tantamount to success if I want to use overcomplicated vocabulary. But you know, it's important. It's important, right? And let's make important the word of the day. Keeping it simple. Important. Important is the word of the day, right? But I'm going to stop this recording and then kick on over to the tech assignment and walk you through that.